Hello everyone. So what I'm gonna do in this very quick tutorial here, I'm gonna go through one slide of the protein structure lecture, which many of you are confused a bit with the content of. So what I'm gonna do, I'm gonna clarify one point, which is about the formation of tertiary structure and the impact of different R groups and the bonds they can make on the overall delta G. So the point of the slide, which I'll show you in a second, is that both hydrogen bonds and hydrophobic interaction, they do both contribute. They are the main contributors to the formation of the tertiary structure, more than disulfide bridges and so on. But among these two options, the hydrophobic interactions are the ones that have a biggest contribution. So the folding of proteins to mask the hydrophobic nonpolar R groups has a bigger impact overall in the delta G of the system, and therefore bigger impact in a sense that it decreases the delta G more than the decrease that you observe with the formation of hydrogen bonds or polar interactions. So, and this because the change in enthalpy and entropy with hydrophobic interaction is largest, so the decrease in enthalpy is largest with hydrophobic interaction compared to hydrogen bonds or polar bonds, and the opposite for the entropy. Okay, so that's the point that you have to take home from this slide. So let's go through the reasoning again. This is the slide, the one, the 80 out of 80 students are, no, I'm just joking, but many of you have a little bit of a hard time. So the point here is, if you have polar R groups here that can form hydrogen bonds or polar interaction here causing the folding, in this case you have non-polar R groups folding the protein as well. Now, this is the one, the non-polar R groups have a largest impact overall in the delta G. Okay, so to understand that, we have to see what is the impact of both scenarios here on the change in enthalpy and the change in entropy, which combined together are those factors that change the delta G. Okay, so let's go for it. First of all, what we have to understand is what is, and that's the key part here, is what is the enthalpy level in the two scenarios at the beginning, before the folding takes place. So let's compare to determine, give us some sort of estimate of the enthalpy and entropy in the two scenarios of the unfolded peptide with polar or non-polar amino acid. Let's try to determine by comparing to what would be the level in a pure aqueous solution. So let's start with the polar peptide. So this peptide, and both peptides would have, obviously to be comparable, they would have the same number of amino acids, with the difference just being that this peptide here has polar R groups, the other one has non-polar R groups. So what would be the starting enthalpy and entropy in this case? Obviously, once you have this unfolded peptide in water, is taking some volumes, right? The water molecules that find themselves around this peptide, right, would have to break some hydrogen bonds with other water molecules. So there will be a reduction of hydrogen bonds. However, some of them could be replaced, in this case, with bonds with these polar groups. The reason being that there are polar R groups, so this can be formed. Overall, though, in general, most likely the number of bonds in this scenario right here, so where the peptide is in with the polar groups is in water compared to pure water, there will be some decrease overall in enthalpy. The reason being that there will be overall less bonds in this scenario compared to the pure water. Okay, it's similar to the scenario, if you want, that you have when you add salt or even hydrophobic compound, but in this case more comparable to salt because these are polar group. So the enthalpy, since there are less bonds here, so less bonds that will need to be broken to separate these molecules, the enthalpy at this point will be higher. Similar, when you always have a problem with this, figuring out where is higher or lower enthalpy, is similar to the scenario of water going from solid to liquid or from liquid to gas, where the enthalpy is increasing. In fact, it's an exothermic type of process, right? Where you have more bond, comparing, for example, liquid water to gas, you have bonds between water molecules in liquid water and no bonds in the gas form of water, in the vapor, right? And enthalpy is going up. Less bond, in this case, like hydrogen bonds, higher enthalpy. Same thing here. Less hydrogen bonds in this scenario compared to this scenario, enthalpy is a bit higher in this scenario right here. What about entropy? Well, entropy here is very good for these polar groups. They find themselves separated. However, there is the entropy of water that somehow gets reduced. Even though these are polar groups, right? So these water molecules overall they have some freedom to move around because they can form bonds with other water molecules but also with this polar group, so they can rotate. Still, is never as good. The freedom of this water molecule is never as good as it will be in an aqueous solution. So there is a slight decrease in entropy once this peptide has been dissolved in water. What about the second scenario here, where you have non-polar groups? Well, looking at the enthalpy right here. So the bonds, number of bonds here, same thing. They get disrupted in this scenario right here, right? The difference between this peptide with polar groups and this peptide with non-polar groups is that in this case, the bonds here that between water molecule that were present here, which now have been disrupted, they cannot really be substituted by any bonds with the non-polar R groups, right? So in this case, now the enthalpy is going even higher compared to the first scenario right here. Slightly higher, but higher. This is more similar to non-polar molecules. Remember when we were going through the scenario of solvation of amphipathic molecule or non-polar molecules. So enthalpy in this case is increasing more compared to this solution. And what about entropy? Well, entropy too is decreased more. Why? Because now these water molecules around this peptide, they can't really turn around that much anymore like this one, because basically they can only form bonds with other water molecules. When they turn around, they cannot form. So they're kind of constrained more in a specific orientation, right? Therefore, their freedom is reduced more in this scenario compared to this scenario, and therefore the change in entropy from here to here is even higher. So the entropy has been decreased more in this scenario compared to this. Okay, so this will be the starting scenario right now of the two unfolded peptide. You're starting with a scenario here where the enthalpy overall is still higher than in this scenario here, and where the entropy in this scenario with polar groups is higher than in this scenario right here. Okay, so let's move on now to how the enthalpy and the entropy becomes after the folding of this peptide. So that's the starting scenario we just discussed. What's going to happen once this peptide folds, and therefore these polar groups are binding to each other, exposing other R groups here, usually polar groups in this side, to the aqueous environment. And when, in this scenario, the non-polar groups form hydrophobic interactions here, again, exposing the other R groups here, polar groups, to the aqueous environment. So how will be the enthalpy at this point compared to right here? So now, how would it change? Well, overall, this enthalpy shouldn't change too much, if you think. So these polar groups could form the bonds with the water. Same thing, these R groups here in this folded peptide. However, the overall surface, if you want, that the water molecules find themselves binding to non-water molecule would be a bit less in this case. This peptide becoming more compact, right? So these water molecules now, some of them can form more water bonds, more hydrogen bonds with other water molecules, right? And so I would expect that the enthalpy in this case, gonna go a little bit lower than it was at the beginning. A little bit more hydrogen bonds between water molecules in this scenario. Therefore, we need more thermal energy to break this molecule free. The enthalpy is going lower. What about in this scenario right here? Well, so here, these water molecules could not really form many bonds or no bonds at all with these non-polar groups, right? But now these non-polar groups have been masked and now they're exposed to polar groups. So they can start forming bonds. So the change here, so now they find themselves able to form bonds similar to the scenario we have right here. So the enthalpy here should end up similar to the scenario right here, where you have these R groups. Now there are no more non-polar groups here that constrain, that limit the number of bonds to this water molecule. So the enthalpy should end up roughly to the same level. So what about the change in enthalpy at this point? Well, you can see now the change in enthalpy here is going down, absolutely, which is great for the delta G. It's going to make the delta G lower, or the change in delta G lower, so more negative. But in this case here, the change in enthalpy not only is negative, but is more negative than when you have polar R groups folding. Okay. What about the entropy in this case? Well, these water molecules had some freedom, but not complete freedom, because again, they cannot form the same amount overall of hydrogen bonds compared to when you're in pure water. Now, once this folds around, you would have a little bit less of this molecule being constrained around this. Excuse me, this was forgot to turn off the thing. That's my green pea. So you would have less water molecule now being constrained around here, right? Because the surface is going to be less, right, when it's compacted compared to this. So you have a more water molecules that are free to move around, and therefore the entropy should go higher. These plus minus are all relative signs, just to give you an idea if it increases or not. Now, what about this scenario right here? Well, it's fairly similar, but in this case, though, you're starting from a situations where you have a lot of limitation, a lot of constraint to the freedom of these water molecules, and now they're exposed to polar groups right here, and so they have definitely more ability, more freedom to move around, higher entropy as well, probably similar to the scenario you would have here, because if they both have polar R groups now on the outside, that should be fairly comparable here. Okay, assuming again that the size of this peptide is the same than this one. So what about the change? Well, the change now is different though, because here you're starting from a different level. This is much lower entropy to start from compared to the scenario where you have polar R groups, right? So the change here, yes, there is an increase in entropy, great. It favors what's happening, the folding as well, right? In both cases, the folding is favored. But in this case, the change in entropy, it's even bigger, right? So now if we combine these two changes together, figuring out what happens to the delta G, right? This is the formula, is the change in enthalpy minus the change in entropy times the temperature of the system. Temperature will be the same in both scenarios. Now, if you take into account these two components, you can figure out that the change in delta G in the presence of non-polar R groups here. So based on the hydrophobic interaction with them, will be much bigger. So the lowering of the delta G in this scenario is much bigger than when you have polar R groups based on the combination. Again, I want to stress both polar groups and non-polar groups contribute to the formation. They are the main contributors, okay, to the formation of tertiary structure. The point of this slide is that the non-polar R groups, through their hydrophobic interaction, actually have a larger impact than the polar R groups in the formation of tertiary structure. So I hope that now all of this is clear for everyone.